Hello. There we go. Right. Yes, so today I'm going to give you a kind of deep dive into Sendable. And hopefully by the end of the talk, you'll know why Sendable exists, what exactly it is, and how you can use it in your apps to write safer code. So, hi, I'm Tim. I run a company called Broken Hands, and we do server-side Swift training consultancy, so basically helping clients ship server-side Swift applications around the world. But I'm better known as being one half of the Vapor core team, so responsible for building, maintaining, and evolving the Vapor framework. And a lot of today's talk is based on the experiences that we've had trying to adopt Sendable in our code bases. I sit on a couple of work groups for Swift, so the website work group, which is responsible for Swift.org, and the server work group. And the server work group is very interested in Sendable, and we've been pushing Sendable in the ecosystem and trying to adopt it. I'm part of the server-side Swift team at Codeco, and I organize a couple of meetups in the UK and the server-side.swift conference, which I'll have a little bit on right at the end. And you can find me on all of the socials as 0xtim, so if you have any questions, feel free to reach out and ask them. So, why does Sendable exist? And in order to answer that question, we need to go right back to the start and look at Swift itself. So Swift was released back in 2014 on stage at WWDC, and it was designed as a successor to Objective-C. And it had four main goals as a language. It was supposed to be fast, modern, safe, and interactive. And it's that third one, safety, that I really want to nail down to today. Because Swift has a lot of features built into it that make it a really safe and good language. For instance, we have optionals, which means that errors like null pointer exceptions just don't exist. There's a whole class of errors that you get in other languages that just aren't possible in Swift. Swift has got really good memory checking and bounds checking. So some other languages, which I'm not going to mention any names, will just consume as much memory as it possibly can before you stop it. And it's the developer's responsibility to know when to stop it. And we see all of these bugs, such as use after free and security issues and memory issues, caused by using memory unsafe languages like C and C++. Whereas Swift doesn't have those problems. And you have to try really, really hard and opt into unsafe parts of the language in order to fall into those traps. Swift has also got explicit error handling. So if you have a function that throws an error, you have to explicitly handle that and mark it with a try. And it's very clear when you're reading the code about where those errors are thrown. And you have to handle them. Whereas some of the languages, you kind of just have to guess when it's going to throw an error, which makes it hard to reason with. And Swift is also strongly typed and statically typed, which means that when you're dealing with variables and functions and properties, you know what type they are. So if you're dealing with something that's an integer, it is an integer, and it cannot be anything else. If you're dealing with something that's a user, it's a user. Whereas other languages, it's kind of a user, but you can add a user to an integer and just see what happens, which makes it very easy to write unsafe code. So Swift's whole ethos is to stop undefined behavior. And I don't mean stop all crashes, because sometimes crashes are good. So if you're writing a banking app and you detect you're running in a jailbroken environment, crashing might be the safest thing to do. If you're writing a very low-level program for the secure enclave in Swift, which does exist, and is written in Swift, if you encounter some memory corruption or security issues or signing issues, the safest thing to do is to crash out before you make any other problems bigger. But we want to stop those unexpected crashes and undefined behaviors. And the whole ethos is to move all of those errors that you get at runtime in many other languages to compile time. It's the whole ethos of shift left, because we want to know about these errors and these problems before we ship our app and before it goes into production, so we don't have to quickly revert it out. Whereas other languages, you kind of YOLO it to production and see what happens. But there is one class of errors that Swift is still susceptible to, which is data races. And I'm sure many of us have seen problems like this, where you get an exec bad access error when you're trying to do something that's fundamentally unsafe and introduce a data race. And when I say data race, what I mean is when two pieces of code on different threads try and access a shared resource at the same time. So if we have code on thread A and code on thread B, and they both try and access this shared resource, if one's writing whilst the other's reading, or they're both writing, this is bad, because which takes precedence? Which wins in this situation? And this is an undefined behavior, and the safest thing for the Swift runtime to do at this point is to crash, because otherwise you introduce unexpected behavior. And this isn't a problem that's exclusive to Swift. Almost every other language has this issue. So here is some documentation for Boto, which is the AWS SDK for Python. So if you go to one of the chapters, and then go to one of the sections of that chapter, and then go to one of the subsections, and then go to the page and scroll right down to the bottom of the page, and then look at the last section, and then actually read it, you'll notice this little sentence here, which says, resource instances are not thread safe and should not be shared across threads or processes. And it's up to you as a developer to know where these problems are, to know that this code is not thread safe, and you need to manually handle that. And you need to know how to handle it, and need to know that your code is safe, and audit it, and make sure it's safe, and stay safe as you evolve it. And all these things that you have to take on as a developer. But why? Why do we have to do it? Why, instead of reading the documentation, which we never do, just knowing about it, or actually reviewing a code, why can't the compiler tell us when we're doing something that is inherently unsafe with data accesses? And that leads me very nicely onto what Sendable is, because that's what Sendable is. Sendable is a way of annotating your code to tell the compiler, and for the compiler to check that you're writing essentially thread-safe code. So it was introduced in the Swift Evolution Proposal 302. It's a really in-depth, very well-written proposal. If you're interested, go and read it, because it explains all of the history, all of the backgrounds, all of the thoughts behind it, and it is very in-depth. But the kind of one-line elevator pitch is that Sendable provides compiler guarantees of data safety in concurrent environments. And this is basically means that the compiler will be able to go through your code and tell you when you're doing something that's safe and allow it to pass, or warn you or throw errors when you're doing something that isn't safe. And it's kind of similar to Rust memory safety, in that it's not similar at all, but it has the same goals. So both Rust and Swift have the same goals of writing memory-safe code. They go about it in very different ways, but it's the same ethos behind the design. And you can essentially think of Sendable as thread safety. So if a type is annotated as Sendable, then essentially it's thread safe. And I'm going to caveat this, because threads are not the same as tasks in Swift concurrency, and any compiler engineer that hears me say Sendable is the same as thread safety will get very annoyed. But if you want to think about it in an easy way, that's the way to think about it. And it goes back to this ethos of shifting left, of moving all the runtime errors to compile time errors. So the compiler will now tell you when you have data races in your code, so that you can't ship them to your users, instead of getting them at runtime when it crashes. So how does this work? Well, if you actually go and look at the Swift source code, you can see that Sendable is just a protocol. It's a very special protocol that has a lot of special things in the compiler, but it is just a protocol that you can adopt in your types. And you just annotate your types with it. And it kind of works as layers. And you can think of it as a pyramid or an onion, but if the bottom layer is Sendable, and if your bottom type is Sendable, then anything using that type can also be Sendable. And then anything using that type can also be Sendable, and anything using that type can also be Sendable, and so on and so forth. And sometimes it can feel like you're just pulling a never-ending thread, because as soon as you introduce Sendable to one type, that ripples down the entire code base, and everything else needs to be Sendable. But it's very similar to throws and tries in Swift and async await, in that we have to be explicit about where we're using these features, because it makes it very easy to read and very easy to reason about. So when you're going through your code, or when the compiler's going through your code, this is the kind of steps that it takes. So let's say that I have an address book. And this has a single property, which is an array of people, or array of persons, that is people, and it's annotated as Sendable. So when the compiler's coming through, it will see, okay, address book Sendable. Let's make sure it is Sendable. I'll have a look at the types. this has a single type, which is an array of person. Now, array is in the standard library, and that is sendable as long as the things inside it are also sendable. So the compiler will go through and look at person. Now, person is also sendable, so this is good, and it contains two properties. It contains the date joined, which is the date, and this is part of foundation, which is marked as sendable, so that's good, and person data. So we need to go and have that. So we have a look at person data. This contains three properties. A name, which is a string, part of the standard library, that is sendable. The age, which is integer, again, part of the standard library and sendable, and another string. So the compiler knows that person data is now sendable, so it can now bubble up and see that, okay, well, person data is sendable, so person is now sendable. And because person is sendable, address book can now be sendable. So many of the types inside the standard library are just sendable, so things like dates and integers and strings and UUIDs, and some of the types in Foundation as well. Basically, the base types that we use to define our own types are automatically sendable. And this is because value types in Swift are, by default, sendable. So if you have a struct that contains other sendable types, then this is sendable. And it's very easy to mark it as sendable because there's nothing to do. Because we get to use value semantics and copy on writes, there's no inherent unsafety with these types. Because if you try and write to it from two different things, you get a copy of it. And sendable is implicit inside the same target. So if you're writing an app that has lots of different types, such as person data, this will automatically be sendable for you, and you don't have to tell the compiler that it is sendable. But if you're writing an API or a package and you want to expose sendability to the consumers of your package, you need to manually opt in and make it explicit. And this is to stop you breaking the API accidentally going forward. Protocols can be sendable as well, because again, it's just another protocol, so you can just conform that protocol to sendable. Generics work in the same way. They're sendable as long as their types are also sendable. So this is how things like arrays work with and collections. And you can mark closures as sendable as well, in the same way that we mark them escaping. And the compiler will ensure that anything passed into this closure is also sendable, so that it can be passed around and used in a thread-safe way. So this is really easy. We just kind of whack sendable on everything. Everything's gravy. All good, as to explain the English expression there. Well, not quite. Because I haven't talked about reference types yet. So in the simple case, where you have a class that is final, so if I can get my little pointer to work here, there we go. So if it's final, then you can't subclass it. If it only contains immutable types that are lets, and they are also sendable, then again, you can just mark it as sendable, and everything's fine. Because there's no mutability in this type, so it's impossible to be thread unsafe. But that's about as far as reference types go with sendability, at least of the easy types. And most of us writing apps want to use reference types for their semantics. If you're writing Swift data models, they have to be reference types because it relies on reference semantics. So we need to make these types sendable in order to pass them around or have ways of dealing with that. So, for instance, here's a very obvious model for a person that contains a name, an age, and a phone number. And we want to rely on reference semantics to be able to pass this around without having duplicates and copies everywhere. And this is kind of where it starts to get a little bit complicated. So, how do we go about solving this? So let's say I have my address book that has the array of reference types persons. In order to be able to use this address book safely, there are a number of options that we have. Option 1 is use main actor. And actors are a way of synchronizing state internally. So the compiler will ensure that any accesses to people inside are synchronized, and any accesses outside are also synchronized. So you'll notice when you're calling functions that talk to people, you'll have to mark these with a weight, because the compiler is synchronizing the access to the state. Option 2 is use actor, which is essentially the same as main actor. It's just not scoped to a single executor. But actors aren't always the best solution. Sometimes they're not what we want. Sometimes it's impossible to add because it will ripple async await throughout your code. And sometimes we just can't adopt them. So other options are using your own locks and essentially simulating what actors do. So in this instance, we have our array of people that's made private, and then we have a lock. And then any accesses to adding or getting a person is synchronized with that lock. And because this state is handled manually by us, we can then use unchecked sendable to tell the compiler, don't worry, this is safe. And unchecked sendable is kind of like your little note to the compiler saying, don't worry, I know what I'm doing, everything's fine. And it is a useful get-out clause in some instances. However, you need to be really careful when you use it. So I don't know if anyone can spot this, but if we go back to the example we've just seen, there is actually a bug in here, and it is unsafe. Does anyone know what it is? Person in this instance is a reference type, which means that the address book itself is safe, but the array itself is not, because you're storing reference types inside that array. So to demonstrate this error, let's say I create my address book. I'm then going to create a person, and then pass that person into the address book. I'm then going to pass the address book into some asynchronous function that's going to do some work later. And this is all fine. So in this instance, store address book async will take a sendable type. Address book sendable, so this is all fine, and there's no problems. However, I'm still storing this reference to person, which means that I can mutate person at the same time that this asynchronous function could also be trying to read or mutate person. And this is a crash, because this is a data race, classic data race issue, because you've got two threads accessing the same data at the same time. And if you try and use actors, you will actually get a warning at this point, because you're passing in a non-sendable type into your actor. So this is where kind of using default types, safe things, and not using unchecked sendable will really pay dividends. Now in this instance, on screen, I'm actually creating a person, passing it straight into the address book, and then not using it again. So this actually we know is safe. And in Swift 6, this will actually be okay, because there's a new Swift evolution proposal, 414, which is about region-based isolation, and this will start to solve some of the problems. So because here I actually have person and then pass it in, this is actually all safe, and the compiler can now infer it in Swift 6, but it can't in 5.10. So what are the options that we have for making safe mutable values? Well, one of them is to actually lock each individual property. So in the server world, we have something called a neo locked value box. And this essentially wraps a property and synchronizes all accesses to that individual property via a lock. So if we go back to our reference type person, instead of having a string, I have a neo locked value box string. And then any accesses to that property are done via a lock, and this makes it safe. And because they're also locked values, I can make them lets, and because it's now a final class, everything's immutable and everything's sendable, I can now make this actually sendable, and this is fine. And so because I can do this, I can then do the same thing with my address book, and do the same thing with people, and then my address book is sendable, and I can pass this around without any issue. In Swift 5.10, you have another option, which is to use non-isolated unsafe. So because we know that person is safe because we've made it sendable, what we can do is actually mark this with non-isolated unsafe, and this tells the compiler, don't worry, I know what I'm doing, kind of like unchecked sendable, but without the whole blanket, make everything fine. And then any access to people we can synchronize via lock, and everything's fine. One other option is using something like a neo loop bound, and this essentially ties any accesses to the type to a specific thread or event loop. So you can have this on the server world. In the iOS world, you can use a similar thing for dispatch queues. And this ensures that the types are created on the same event loop and on the same thread and only accessed on that thread. But you will get a runtime crash if you try not to. So it's something to bear in mind. And then we can just wrap our unsafe type in this. And then because it's, again, immutable and sendable, address book can be properly sendable and all fine. So these are various different options that you have for making your type sendable. But generally, if you can, try and use value types and structs and enums to start with, and then if you need reference types, use them later. So in order to kind of start adopting Sendable, you need to go on a bit of a journey. So if you're writing Xcode projects, such as iOS apps or Mac apps, there is a option in the Swift compiler flags. So if you go to your build settings and go to the Swift compiler flags, you can find this thing called strict concurrency checking. Turn it to complete, because this will turn on all the warnings that you'll get in Swift 6. So Swift 5.10 now has all of the Sendable checking and will provide full data isolation in Swift 5.10. If you turn it on to complete, you'll get all of the warnings of where your code is unsafe. Swift 6 that's coming in the future is a bit cleverer about things that are safe but currently look unsafe, so you'll get less warnings in Swift 6. If you're writing a Swift package, you can enable this using the experimental feature flag. And then once you've done this, you'll start to get all your Sendable warnings. And you'll get some warnings, and when I say some, I mean a lot. And this was the Vapor project when we turned on strict concurrency checking. So we had 3,000 warnings that we needed to fix. But thankfully, a lot of these were the same warning over and over again because one type wasn't safe. So as soon as that type was fixed, then a lot of these warnings disappeared. So once you've done this, you'll see that you start to get some errors of stuff that is really bad and you really shouldn't be doing. So in this instance, we're passing an immutable unsafe type into a closure that is sendable that we can then mutate anywhere. This is really bad, and the compiler's telling you, don't do this, don't be an idiot. Most of you will probably see lots of warnings like this. So you get things like reference to captured var in concurrently executing things because application is not sendable, or capture of configuration with non-sendable type, blah, blah, blah. So as soon as you start making things sendable, you'll start to see these warnings disappear because your code is now safer. And Sendable hasn't been an easy journey for Vapor. We started adopting it as soon as it started coming out, around 5.7, 5.8. It prompted a lot of discussions because we managed to break the compiler quite a bit. So we had one discussion around a compiler crash that was a bit busy between many of the Swift engineers and Vapor engineers. But these things are now kind of mainly fixed. So in 5.10, it's actually quite a nice thing to start adopting. It's not easy, but it's doable, and the compiler doesn't crash anymore. So one of the last things I want to talk about is maintaining your API. So if you're writing if you're writing an application, you can start adopting Sendable. It doesn't matter because you can adopt your code. If you're writing a library, you kind of need to be a bit more careful about things. Because as soon as you start making your code sendable and changing it so that it can be sendable, you might find that you start breaking your API. And generally when you're writing libraries, you don't want to break your API, even though it's a real pain. It'd be much nicer if we could just break it constantly. And you want to try and make things backwards compatible, so that anyone adopting your code doesn't have to make breaking changes constantly. So one of the tricks with this is app pre-concurrency. So this is an example from our WebSocket library that we made sendable. And in order for us to do this, the callback you can see here had to be sendable. But this will introduce a warning for anyone using this that isn't actually using a sendable callback, even if it is inherently sendable and they just need to annotate it, which is quite annoying because if you do a library update and all of a sudden you have 100 warnings because your code now isn't sendable, it can be a bit of a pain. So by using app pre-concurrency, this tells the compiler that this API existed before concurrency was a thing, so don't start warning users if they're not up to date. And this is quite a nice little thing to turn on. If you have strict concurrency checking turned to complete, then they will get warnings because it shows them all the warnings, but for most people they won't. You can also do the same when you're pulling in libraries that aren't currently updated. So you can use the app pre-concurrency import console kit, and where you're getting warnings for types inside these libraries that aren't sendable yet, you can say to the compiler, this hasn't been updated yet, don't warn me about these errors or warnings. So if you're pulling in dependencies that aren't sendable yet and you're trying to make your code sendable, this is quite a nice little fix to remove those warnings. One of the issues that we came up with in Vapor was trying to maintain our public API. So inside our request type, it's a reference type, it's a class. And we have all these mutable properties, such as method and status and body, that we now need to make immutable so that we can make our type sendable. And we can't change method to be a neo locked value box because that breaks our API. And anyone using method would then need to change their code. And we don't want to make breaking API changes so often. So one little trick is to turn it into a computer property. So we have a private property that's a neo locked value box internally, and then the public property is now computed, and we get and set and access it via that lock. And this is a nice way of keeping your API the same without breaking it, but still making it safe. So nice little trick there. Okay, so to recap, remember, Sendable provides compiler guarantees of data safety in concurrent environments. So it's a way of telling you, the compiler telling you when you're doing something that isn't unsafe. It's quite easy to adopt, or the concept is quite easy to adopt. And if you have structs and enums, it's very easy to adopt. If you have reference types, it gets a little bit harder. But it's a good way of ensuring that your code is not going to be susceptible to data races. There are still some changes in Swift. So Swift 5.10, as I mentioned, has all of the sendable checking. You can turn it on if you want to. But it's not as clever as the Swift 6 compiler in telling you when things are actually fine, even though they don't look fine. And there are a lot of new proposals currently going through the process to ensure that adopting Sendable is going to be easier when Swift 6 comes out. And there are quite a few more proposals that are still going through the proposal reviews. So these are all the current proposals on Swift Evolution forums that are purely about Sendable and isolation. So don't worry too much if you try and adopt it and it can't happen yet, because there are all these things that are coming that will make your code easier. And WWDC is coming out next month, in about a month's time, where we're going to see Swift 6. And in Swift 6, all of these warnings that you currently see with strict concurrency checking are going to be errors. So Swift 6, if you're using the Swift 6 language mode, will not let you write unsafe code. You will get compiler errors. So you should start looking into this now, and as soon as Swift 6 comes out, to ensure that you can start writing your code and use the Swift 6 language mode. Don't worry too much, because there is the Swift 5 language mode. So by default, if you have existing code, you need to opt into the Swift 6 language mode. So your code will continue to compile fine, don't worry. You don't have to update it straight away for day one. But it doesn't mean that your code isn't unsafe if you're not getting these errors. Your code is currently unsafe. The compiler just isn't telling you about it. So thank you.